All right, so here we go. Last section of nuclear chemistry. Okay, so we're going to describe the process of nuclear fission and fusion. Now, those terms will be defined, but the one thing I really want you to understand, in nuclear reactors, many people believe like somehow the energy of the nuclear reaction is harnessed. No, actually, what a nuclear reactor does is when energy is released, it's let off as heat. Hence, you hear bad things when there's a meltdown because you're not controlling the reaction of the heat. But you're basically boiling water to produce steam that is there to turn a turbine generator. So it isn't the actual process of nuclear fission, okay? It is the process of heat being generated that actually creates electricity for nuclear reactors. All right. So, nuclear fission, a large nucleus is bombarded with a small particle, okay? The nucleus splits into smaller nuclei and several neutrons. So a huge amount of energy is released, and the energy is in the form of heat, okay? The energy generated by splitting the atom is called an atomic energy. So if we think about the atomic bomb, what really happened is we split nuclei up, releasing a massive amount of energy, which in turn in heat and pressure is and radiation is what actually destroyed buildings and harmed people. So when a neutron bombards U-235, uranium-235, an unstable nucleus of uranium-236, okay, so if we're hitting it in the nucleus, and this undergoes fission, so it splits it, it's like unstable, it's like, oh my gosh. So the nuclei are produced in such as Kr91 and Pa142 as it splits, okay? Well, and if we think about this, it makes sense. The neutrons are released to bombard more U-235 nuclei, and this chain reaction starts. All right, so if we look here, handy dandy pen, right? Always got to use that. So, neutron, boom, into the nucleus. Uranium's like, oh, I don't like this at all. It's like shaking and everything. Okay, finally, boom, one nucleus breaks up, all right, sending out more neutrons to other uranium nuclei, and the process repeats itself until all of the uranium is exhausted. All right, so it's a catalytic response. Once it starts, it keeps going until the energy is wasted, or until you can remove the source, okay, the uranium. So if we could determine the mass of the products, krypton, barium, and 3 neutrons, we would find that their total mass is slightly less than the mass of the starting materials. The missing mass has been converted into enormous amounts of energy, consistent with Albert Einstein's theory of energy equals mass times the speed of light squared. So we can prove this. Okay, a chain reaction occurs when a critical mass of uranium undergoes fission. A rapid increase in the number of high-energy neutrons are available to react with more uranium. To sustain a nuclear chain reaction, sufficient quantities of U-235 must provide a critical mass in which almost all the neutrons immediately collide with more U-235. If we were able to remove the U-235, what would happen? Well, the reaction would stop. And this is a good explanation of what I was talking about. Splits off, splits off, splits off, and then boom, 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 and it just keeps going and going and going. So, supply the missing atomic symbols to complete the equation for the following nuclear fission. All right, so bombarded with a neutron, boom, breaks up. So what are we going to do? What are we going to look for? All right, what's missing here? Well, it's going to be ZR97. Okay, well, if we go 97 plus 137, what does that give us? It's going to give us 234. Right? Yeah. And then we add in one more neutron, and that will give us our total of 235. Nuclear fusion occurs at extremely high temperatures, so it doesn't really occur here on Earth necessarily. All right, it occurs at over 1,000,000 degrees Celsius. Okay, so it combines small nuclei into larger nuclei. So rather than splitting, we are now fusing together. It releases huge amounts of energy, and this is why it's so sought after. A term called cold fusion. Could this be happen at room temperature? Which we still have not been able to make happen. But it continuously occurs in the sun and the stars. And if we think about how life on our planet works, we need the sun's energy in order for us to survive. So scientists expect less radioactive waste with shorter half-lives from fusion reactors. So if we look at this nuclear fusion, you've got a pipe carrying heat exchangers, hot gas, magnetically compressed plasma. All right, you bombard two hydrogen atoms together. It's going to create a helium atom releasing one neutron and then energy from it. Okay. So if we look at nuclear power plants, fission is used to produce energy. The quantities of 235 is held below its critical mass, so it doesn't explode. Control rods in the reactor absorb neutrons to slow the fission process, to control it. And the thing that happened in Japan is those rods kind of melted and sealed in, so they couldn't be removed, to stop a partial meltdown of those reactors. The heat produced in the fission process is used to make steam that drives a generator and produces electricity. Okay, so nuclear power plants supply about 10% of electricity in the United States. Nuclear power is used in Europe more widely, Japan more widely. In the United States, we tend to have a stigma with nuclear electricity because of when it goes bad, it does go bad. But we actually in Ohio have the David Bessie power plant. I think it's near Port Clinton. I know it's in the Northwest Ohio region. So we do get some of our electricity through nuclear power. All right, and here's a nice diagram. Okay, we've got our control rods to control the reaction. We've got the reaction occurring, generating heat. Steam is being generated. Goes to a turbine. The turbine turns, the steam then condensates, cools, and the reaction in the generator starts over again. And hot water is also dissipated into a waterway of some sort, just for overflow. Okay, because steam, obviously being a gas, will have a higher volume than liquid. So indicate if each of the following is a nuclear fission or nuclear fusion reaction. Well, a nucleus splits. So what is that? That's going to be fission. Large amounts of energy are released. Fission and fusion. Small nuclei form larger nuclei. Fusing together. Fusion. Hydrogen nuclei reacts. What's that? That's going to be fusion, right? Because the hydrogen create helium. Several neutrons are released. Well, that's both fission and fusion. Oops, that's just fission. One neutron is released in fusion. I apologize. There we go. So, yeah, these are the concepts that you should understand for radioactive chemistry, nuclear chemistry, and you might want to write this map down so you kind of understand what's going on. Thanks.